Yeah.
Mabuhay! Welcome to the Filipino Science Hub.
Let me try that again. Yep, I think people are already in. Something went wrong. No, it's fine, Ma'am Dindy.
It's not playing, Kuya.
It's not playing.
Yeah.
Can you, Ma'am Dindy, share? There's something wrong on my end.
I think it's okay. We can just
Wait a sec.
yeah. Yeah, I can share. Just make me a host.
Yeah, wait.
Okay.
I think.
How you
How about
figured it out? Okay, perfect.
Yeah, it's starting now.
Okay.
Mabuhay! Welcome to the Filipino Science Hub. Thank you for your continued support to this online platform. To our new participants, thank you for checking us out today, and we would like to officially welcome you to the FilSci Hub family. Before we start the webinar, I would like to share some house rules in order to facilitate a smooth session. For our Zoom participants, we would appreciate it if you could turn your audio and video cameras off during the webinar. If you have questions or comments, feel free to type them on our Zoom chat box or YouTube live comments, and we will try to accommodate as much questions as possible. After the talk, we will have a 30-minute Q&A where the Zoom participants will have the opportunity to ask their questions live. For those who would like to receive a certificate of participation, a Google form link will be posted on our Zoom chat box, YouTube live comments, and YouTube video description towards the end of the webinar. Again, welcome to all our Zoom participants and YouTube live viewers. For those who are new and may not be familiar with who we are and what we do, allow me to share our mission and vision in the next few minutes. Filipino Science Hub is an online platform founded by our CEO, Filipino scientist Dr. Jeffrey Camacho Bonquin back in 2012. Currently, we are a registered nonprofit organization based in Houston, Texas, United States. Our mission is to promote STEM education and the culture of research among students and teachers in the Philippines and abroad. Our current global leadership team is comprised of volunteer Filipino scientists, seasoned STEM educators, and business executives across the globe. Our vision is to see a technology and innovation-driven Philippines, and we believe that this can be achieved by creating a new generation of well-rounded Filipino STEM enthusiasts. The vision is being carried out via our two major programs, the FilSci Hub Ed program and the FilSci Hub Research University. Through FilSci Hub Ed, we are able to empower and support our teachers by strengthening STEM fundamentals education. We believe that this is important because the more equipped our STEM educators are, the more they can inspire students to pursue a career in science, technology, engineering, and mathematics. The other major program that drives our vision forward is FilSci Hub Research University. This is where we provide tools for fundamentals of research and bring practicing scientists closer to the educational sector. Our official website is www.filscihub.com. This is where you can access all our materials such as webinars, tutorials, modules, virtual lab, and features, all of which are free. We are also present in several social media platforms, so follow us wherever you are most active on to get updated with our web events. Again, thank you for being with us this morning. To officially start our webinar, I would like to turn the virtual floor over to our host today.
So that's me.
That's you.
So back to me. JP, would you mind sharing the Canvas slides, please, so we could introduce Dr. Daniel.
Yep.
All right.
So we're now 33 in the room.
Perfect.
Yep.
Okay, so again, good morning to everyone. Happy Friday, and thank you for joining us this morning. So today we're very excited. We have a very special guest, and it's my honor to introduce to you our speaker for today, Dr. Daniel Whiteson. So next slide, please. Oh, that was your last slide. Okay, let's go to the very first one. All right. Okay, it's Friday, so.
It's Friday.
Exactly.
And I'm still getting into it.
Yes, and it's 5 a.m. wherever you are, so we forgive you. Okay, so Dr. Whiteson is currently a professor of physics and astronomy at the University of California, Irvine. And he got his PhD in physics from UC Berkeley. And he completed his postdoctoral studies from the University of Pennsylvania. So his research interests are in the field of experimental high energy physics, where they're interested in probing the structure of matter and the nature of interactions at the very smallest scales. And this is to understand the fundamental nature of our universe. So he collaborates at Collider Detector at Fermilab, or CDF Tevatron, which currently is the world's highest energy particle accelerator. Again, so he's also a member of the Atlas. There's the meaning there that I don't really understand, but maybe Dr. Whiteson can explain a little bit later. Also a collaboration at the Large Hadron Collider at CERN, which is something French, but it's the European Organization for Nuclear Research. Next slide, please. So Dr. Weissen is actually very popular, so we're really honored he's here. You can find out more about his work from the UCI website, faculty website, but he's actually written several books, and a couple of which I own right now are the books called We Have No Idea, A Guide to the Unknown Universe, and Frequently Asked Questions About the Universe. So he's a co-author with Dr. Jorge Cham, which they also work or host a podcast together called Explain the Universe. And I really look up to them because they're able to simplify complex physics, which is very helpful for chemists.
Thank God.
Okay, so and he's been a TEDx speaker. So yeah, so we're really grateful that he's able to join us today. So, well, without further ado, I would like to turn the virtual floor over to Dr. Daniel Weissen, and let's give him a Phil-Sci Hub welcome. So, Dr. Daniel.
Floor is yours.
Hello, everybody. Very nice to be here. Thank you very much for the invitation. Thank you to everybody who's here and those of you watching on YouTube. I'm very excited to visit with you and to talk to you about everything that we're doing to understand the universe. So let me get this started here. Oops, I'm going to do it this way first. Yeah. Okay. Okay, and so while we have learned a lot about the universe, what I actually want to talk to you about tonight is not what we do know about the universe, but instead everything that we don't know about the universe. And this is the topic of one of the books that I wrote with Jorge. It's called We Have No Idea, A Guide to the Unknown Universe. And you might read science books if you're interested in science, and a lot of them tell you about all the incredible things that science has figured out. But for me, the most interesting thing about science are the future discoveries, the things that I may not discover, but maybe you will, or your children will, the things that we do not yet know about the universe. Because to me, science begins with discovery, and discovery begins with understanding what you don't know. So this is a book I wrote together with my friend Jorge. He's the author of PhD Comics, which is a very popular comic strip read all around the world. And this book is it talks about deep questions in physics. What is the nature of the universe? How big is it? But we try to do it in a way that's approachable, that's not too intimidating. And so Jorge put a lot of his really fun cartoons in here. And so all the drawings that you'll see tonight are done by Jorge. I'm not an artist. So he gets credit for all of those. And for me, this quest to understand the universe began when I was just a little kid. And I was learning about the age of explorers, how people, explored up through Asia and then across the land bridge and down into the Americas tens of thousands of years ago. And I thought that must have been incredible to be the first person to go somewhere or to see something. Imagine being the first person to ever see the Grand Canyon. What was that like? Wow, what a moment, right? You're the only person alive to ever have seen it. Or the person who discovered chocolate. What was that like? The first person to ever eat chocolate, or, the first person to eat chocolate while looking at the Grand Canyon. The idea is that these are all firsts in human history. Somebody at some point was on the edge of human knowledge. They were the first person to know something or to go somewhere. And that was really exciting to me. I wanted to explore the world that way. But, growing up in modern times, you feel like maybe that's kind of used up, right? Like, because of satellites and all the technology we have, we've basically discovered everywhere there is to go on the Earth. So exploration sort of felt a little bit used up. And as you look around you and you're amazed at the incredible technology that we've developed, we have these airplanes that can take you around the world in hours, whereas it used to take months. You can download all of human knowledge into a little device that fits in your pocket. I mean, even fast food is getting fancy and advanced these days and getting combined. So you might be forgiven for thinking that there is no more exploration left to do, that we've basically got science and physics figured out, and there's just a few details. That, I think, is what a lot of people think about the universe and our exploration of it. But I'm here to tell you that the opposite is true, that there's a huge amount of exploration left. In fact, most of the universe is unknown. And most of the big discoveries that will ever be made in human history are yet to be made. So let me tell you a little bit about myself. The organizers asked me to also give a bit of a personal introduction. So before I tell you about how I got into exploration and the kinds of questions and discoveries are ahead of us, let me tell you how I ended up here where I am. I was actually born in Israel. My parents moved there because they were in a very religious state in their lives, and they met there and had some kids. But then later moved to the United States. So I moved to Arizona, where my father was working. He was a very conservative and religious, and he was working as a rabbi in Tucson, Arizona. But he had a bit of a crisis of faith, and he decided he didn't want to be a rabbi anymore. And he went to graduate school and became an engineer and fell in love with mathematics and with science and with engineering. So completely changed the direction of his life. And then got a job working at Los Alamos, New Mexico, at the national lab there, doing very technological research. So I mostly grew up in Los Alamos. And not in a very religious household, because my parents had this very strong change in the direction of their life when I was a child. And because he got this education and got this technical job, he also sort of lifted us out of what was essentially poverty we were living in when he was working as a rabbi, into a middle-class lifestyle. And then I got an excellent education at Los Alamos. I went on to go to university in Houston at Rice University, where I learned how to do research. I worked with physicists there to understand how to do particle physics. After I was at Rice, I spent a year abroad. I went to Copenhagen for a year as a Fulbright Fellow, where I got to work at the Niels Bohr Institute. This is where Niels Bohr did his work, and many famous conversations were had. And there's pictures on the wall of, Einstein sitting in the chair that you're sitting in, which is pretty cool place to just sort of be. And I had a lot of fun there for a year. And then I went to graduate school to do my PhD. So I went back. Now I'm in California. And I was there for a few years, and I decided to specialize in particle physics. And in particle physics, you can't just build your own collider. These things, there's like a few of them in the world. They cost billions of dollars. It's not the kind of experiment you do in the lab in any university. Instead, you have to go where they are. And so I went out to Chicago, to Fermilab, where the collider was that was mentioned earlier. And after graduating, I stayed at Fermilab. I did a postdoc at officially working for the University of Pennsylvania, but actually at Fermilab, still doing research there at the collider. So this is the top view of the building at Fermilab in Chicago. And in 2007, I was lucky enough to get a faculty position at UC Irvine, working on this experiment at the new Large Hadron Collider, which was just turning on at the time. So it was very exciting, and I felt like it wasn't my plan at all, but everything just sort of worked out that my career timed very well with when this new collider was turning on. And I did physics there for a couple of years and was having a lot of fun with it. And I thought that the questions we're asking in physics, the kind of work we're doing, are the kind of things I thought a lot of people might be interested in learning more about. So I reached out to Jorge and asked him, like, hey, do you want to do some science communication? Do you want to try explaining some of these things together with me to the general public? And we had a bunch of projects, which led to this book, We Have No Idea, and then another book a couple of years later, Frequently Asked Questions About the Universe. And now twice a week, we talk science on our podcast and make bad dad jokes and explain complicated topics about the universe to anybody who's interested. So that's how I got where I am. But in the end, the thing that motivated me was asking questions. Everything I'm doing now, my research, my science communication, my outreach, is all about asking big questions about the universe. Because I feel like, some people are passionate about making art and some people are passionate about writing. To me, I'm passionate about understanding the universe. It's like an inherent part of being human to me, to be curious about what's around you. And, if you walk down the street and you ask people, like, what's the biggest question in life? You might get, they might say things like this, why are we here? What happens after we die? These are big questions, right? And these are big questions because if you knew the answer, it might change the way you felt about life and how to live it and what it means, right? These questions inform the context of our existence. These are big questions. The problem with these questions is that they're not science questions, they're philosophy questions, which means that you can ask them, you can talk about them, you can smoke banana peels, you might not ever get an answer to the question. Here, for example, is the most famous question in philosophy, the title of the most widely cited paper ever written in philosophy. What is it like to be a bat? It's not a joke, right? The paper itself is basically making the point that you'll never know what it's like to be a bat. You'll never know even what it's like to be another person. So these are fun questions in philosophy to think about. The thing that excites me about science and physics is that there are more questions, the questions at the same level of importance, questions where if you knew the answer, it might change the way you felt about everything. But these are science questions. What is everything made out of? How did the universe begin? And by science questions, I mean they have objective answers that we can learn. For example, the universe began in one way. There is a single true history of the universe, and no other history of the universe is true, right? There is an answer that can be uncovered. And if we are clever enough and work hard enough, we can reveal it, which means eventually, I think, humans will know the answer to this question. Imagine what it'd be like to know exactly how the universe began. It might change the way you feel about your life and how to live it, right? And imagine what it's like to be those humans in 1,000 years or 100 years when we know the answer to this question. What would it be like for them to look back at us and think, wow, what was it like living without knowing the answer to this very basic question about the nature of the universe? Sort of similar to the way we think back to cavemen and cavewomen, looking up at the stars, seeing those twinkling bright objects, but having no idea what they were looking at, right? So many basic things about their existence they were clueless about. We are equally clueless about basic questions about the universe, things like what's everything made out of and how did it all start? We don't know the answers. So when I say that there's a lot of discovery left ahead of us, I mean it literally. There are very basic questions about the universe that we do not know really how to begin answering. Now, I can't talk about all of them today. So let's talk about this one, which is one close to my heart. What is the universe made out of? Seems to me a pretty basic thing to want to understand. Like, what am I made out of? What are you made out of? What's this rock over here made out of? And, when I was a kid, I wondered about this. And I took rocks and I smashed them together and I made smaller rocks. And then I smashed those rocks together and made smaller rocks. And I wondered, how small can you go? At some point, is it not a rock anymore? Is there a minimum size rock? Or can you just keep smashing together to get infinitely small rocks, So I think this is a pretty basic question. I think it's a question people have been asking basically since people have been asking questions, right? You can imagine doing this with basically no technology. And so step back for a moment and think to yourself, like, how would you answer this question? If you were the first person, caveman, cavewoman scientist, to ask this question, look around you and wonder, what's the universe made out of? How would you start to approach it? How do you answer such a big and deep question about the universe? Well, it's not easy, but you might start with a very simple approach, which is just like make a list, look around you and say, what's in the universe, right? And so you're caveman, cavewoman scientist, you're in the universe, your friend's in the universe, there's a rock in the universe, maybe another one, right? As you look around, you realize, oh, well, there's a few different kinds of rocks in the universe, right? And the more you look around, the more you realize, wow, the universe has lots of different stuff in it. It's not just rocks, there's flowers and blueberries and hopefully ice cream. And the more you look, the more you see incredible stuff, weird, interesting, fascinating things in the universe. And you realize the question, what is the universe made out of, is more than just, literally what am I made out of? But it's how do you get all this complicated stuff in the universe? How do you get so many different kinds of things in the universe? Bicycles and neutron stars and butterflies and top hats. There's so many different kinds of things, so much complexity. And so a list is not going to answer your question. A list is not like a satisfying answer. If you asked me, Daniel, what's the universe made out of? And I give you a list of all the things in the universe, you wouldn't feel like, I get it, man. You wouldn't have that moment of understanding. The reason is that that's not the kind of answer we're looking for. The kind of answer we're looking for is not a list that's exhaustive. It's a simplification. We want to boil down all this complexity and explain it in terms of something simpler, right? So how do you do that? Well, the first thing you do is you organize this stuff. You don't just say, I've got a big list. You look for patterns. So you say, well, all this stuff over here is alive and all this stuff over here is, made out of metal, and this stuff over here is made out of rocks. And you can argue about whether, Arnold Schwarzenegger over there belongs in the living thing category or the rock thing category, but everything belongs in a category somewhere. And as you notice that there are patterns, you start to ask questions about why are these things like this? What makes these things like that? And those questions are the critical clues that lead you to understand the way things work at a deeper level, so that you can peel back a layer of reality and see what's going on underneath. And now, of course, we know, fast forward a few hundred or thousands of years, that almost everything in the universe that people have experienced, ice cream and kittens and lava, all of that stuff is made out of a few basic elements, like 100 basic building blocks, out of which you can make basically anything. It's kind of incredible, right? And, this is the periodic table of the elements, of course, we're talking about. You might be thinking to yourself, this guy is supposed to be a particle physicist. Now he's talking to me about high school chemistry. What's the deal? The deal is that I think this is often overlooked. This is one of the most incredibly important achievements in human intellectual history, to say, I can go from basically an infinite variety of stuff to I can explain that in terms of 100 elements. That's amazing. Later on, we'll try to boil that 100 down into 10 or 5 or 2 or 1, but you've gone most of the way already in going from infinite variety down to 100. And it makes you wonder, like, why is that even possible, right? Why is it possible that we live in a universe where all the complexity comes from how you put things together, not in their inherent nature, right? It's sort of like with a few basic building blocks, you can make anything. It's like our universe was designed by the Lego company, and they gave us a few basic bits and we put them together to make all sorts of complicated stuff. The way, with Legos, you can make dinosaurs, you can make pirates, you can make dinosaur pirates, you can do whatever you like. All the complexity of Legos comes from how you put them together, not the Lego thing itself. But think for a moment about if we had lived in a different universe. What if we had lived in a universe where the reason you are you and I am me and cats are cats is not because of how basic bits are put together, but instead they're just like fundamentally made out of different stuff. You know, cats are made out of a little scoop of cat stuff, and octopi are made out of octopus stuff. And there was no other similarity. We could have lived in that universe where the complexity came from the inherent nature of the stuff, not in how it's put together. I don't know why we don't. You know, our universe seems to follow this rule where you can organize basic bits into more complicated things. It's awesome. It's fun. It makes particle physics worth doing. I just don't know philosophically why our universe is this way and not the other way. But it is. And so that means that you can do more than just look at the list of elements, you know, approximately 100, and say, well, that's it, we're done. We can organize them, and we can say, we notice some patterns. You know, some of these things are heavy metals, and some of these things are very active, and some of them are not active, right? And so the periodic table is, of course, periodic. There are patterns there. And those patterns are clues. They're clues that tell you how to dig deeper, how to peel back another layer of reality and see what's underneath the elements themselves. Because carbon and oxygen are not basic units in the universe. Instead, if you zoom in a little bit deeper into the atom, you see that the nucleus has protons and neutrons inside of it, and around that are electrons. And it's the way these electrons fill up their orbitals that totally determines all of the characteristics about the elements. The reason why carbon is carbon and neon is neon is because of those electrons. So what do we learn there? Not necessarily the chemistry of neon. What we learn is that the way to discover what's going on underneath is to look for the patterns that emerge, because those emergent patterns are clues that tell you how it works underneath. They arise from the mechanisms that are going on inside that put the atoms together. So let's keep going. Inside the proton and the neutron are little particles called quarks, 2 up quarks and a down to make a proton, 2 down quarks and an up to make a neutron. And that means something kind of incredible. It means that with up quarks and down quarks, you can make protons and neutrons, add together some electrons, and you can make anything. Like basically everything you've ever eaten is made of 3 ingredients: up quarks, down quarks, and electrons. Not just that, it's those same 3 ingredients in the same proportions. It's not like, oh, you get more, add more electrons, you get lava, add more up quarks, you get kittens. Lava and kittens are made out of the same number of particles. A kilogram of hamster, a kilogram of lava, a kilogram of, you know, birthday cake are all made out of the same number of particles and their proportions. The only difference is how you put them together. So, you know, you ask me to write like a recipe book, every recipe is going to have the same 3 ingredients in the same proportions. It's just kind of tricky to put it together. You need a really good 3D printer. And you might think, wow, we're almost there. Like we started from infinite variety down to 100 elements. Now we're down to 3 particles. We must be around the corner from figuring out what the 1 particle is out of which everything is made, right? Well, the story gets a little bit more complicated before it gets simpler. Turns out that there are more particles out there. While you only need the up quark, the down quark, and the electron to make up birthday cake, there are other quarks that you can make: charm, strange, top, and bottom. And the electron is part of a group of particles we call the leptons, which has the mu and the tau and 3 neutrinos in it. So now we have like 12 particles. But still, we don't just say, here's a list. We say, are there patterns? Because patterns will give us clues about what's going on inside these guys. So there are, in fact, really fascinating patterns among these particles. We organize these particles into 3 generations. And let me tell you why. Well, the first generation contains the particles we're familiar with, the up quark, the down quark, and the electron. In this one, we also put a weird particle called the neutrino. Neutrino is weird, not because it's very rare. In fact, there are 100 billion, with a B, neutrinos passing through your fingernail every second. The sun puts out an incredible number of neutrinos. Why don't you feel them? Why aren't you getting like cancer from all the solar neutrinos? The reason is that the neutrinos ignore you. They pass right through you. They pass right through the whole Earth. They can pass through a light year thick sheet of lead without even noticing. To them, the whole universe is transparent. And that gives you a clue like, there's a lot going on in the universe that I can't see. So those are the four basic particles, the up quark, the down quark, the electron, and the electron neutrino. The other particles are really interesting because they turn out to be basically copies of these first particles. Like the charm quark is exactly like the up quark, it's just a little heavier. And the top quark is like the charm quark, but even heavier. And the same thing is true for the down. It has two heavy copies. And the electron has two copies. The neutrino even has two copies. What's going on? Why are there three of every particle? We don't know. So this is where we are right now, is where we're looking at this pattern of the particles, and we're asking really basic questions that we don't have answers for. Like, why do we have all these particles? You know, you need three of them to make matter. What's the muon for? We have no idea. Why do the particles have two copies, right? That's pretty strange. If you're looking at the theories of physics and you're looking at the numbers in it, you expect to see numbers like 1, maybe 2, maybe pi. To see a 3 in there is very curious, right? Physicists don't think 3 is a deep number in the universe. I mean, I know Catholics find that number very important, and maybe they're right about it, but we don't. We're very curious about why there seem to be 3 versions of every particle, not 2 and not 4, not 8. It's fascinating. We also don't know if this is all the particles. You know, these are 12 that we have found. Are there 12 only? Are there 12,000? Are there 12 billion kinds of particles? These are just the ones we've discovered. We know that some of these don't have a lot of mass, like the first generation is very low mass, and they get heavier and heavier as you go to second and third generation. We don't know why. We don't know. There's no pattern either in the masses. They tend to get heavier, but in sort of very weird ways. We also don't really understand these charges. You're probably familiar with the electron having charge -1. The proton has charge +1, but that +1 comes together in a very weird way. You take 2 up quarks, each of which have charge 2/3, right? 2/3 charge, like what is that? And the down quark is charge -1/3, which adds up, boom, to be +1. You might think, oh, well, that's nice. It's nice. It's also very weird because in our theory, there's no reason why these up quarks and down quarks should add up perfectly to 1, to perfectly balance the electron. Like if you're at the control panel of the universe, you could change the charge of the electron or the charge of the quark separately. They're 2 different knobs. So for them to balance out, for the proton to match the electron exactly, the knobs have to be set exactly to the right ratio. And so is that a coincidence? Or is it a huge screaming clue that these things have something in common we're not aware of? Something deep inside of them is the same, and that forces them to be able to add up in these proportions to make hydrogen and chemistry and biology and life and silly physics books and ice cream, right? Maybe it's not a coincidence. So our goal is to understand why these particles exist and also how they talk to each other, how they push on each other and pull on each other. We have a theory for that. It's called the Standard Model of Particle Physics. It's not really that short or simple yet. Like, here's the equation of the Standard Model of Particle Physics. The goal is to get it so simple that you could like write it in one equation, just, you know, one line of very few number of symbols, and maybe like enough to fit onto a t-shirt. It's sort of like, you know, still a little bit too complicated to fit onto a t-shirt. And it gives me the feeling like that there's something we're not understanding, or maybe we're just speaking the wrong language. It's sort of like this Far Side cartoon where these guys are trying to understand what the dolphins are saying. And because they don't speak Spanish, they are forced to write down, you know, phonetically, habla español. And to them, it's nonsense. It means nothing. If they only spoke Spanish, boom, it would all click into place. And I feel like maybe we're just speaking the wrong language mathematically, that we're trying to write down a description of what we see in the universe, and it comes out really long-winded and cumbersome because we don't see the patterns. We're not understanding how to express it in a simple, beautiful way. Now, the biggest problem in understanding what is the universe made out of is that everything we've talked about, everything we've been studying for the last few hundred years, these mysteries of the particles, that only accounts for a tiny slice of what the universe is actually made out of. Me and you and hamsters and stars and galaxies and everything you see in the universe, literally all that stuff, is about 5% of what's in the universe. The rest of the universe, 95% of the stuff in the universe is something we do not yet understand. So if we're talking about like, are there still things left to discover in the universe? Oh my gosh, 95% of it, we've just gotten started. And you might think, how could we possibly know what we don't know about the universe? Well, we have some really interesting clues. One of them comes from how galaxies rotate. So, galaxies are stars and they're collected together in a big disk and they spin around. And you might wonder, like, well, why do the stars stay in the galaxy? I mean, if you put a bunch of ping pong balls on a merry-go-round and you spin it, what happens? Well, the ping pong balls fly off, right? So why doesn't that happen for a galaxy when it spins? The answer is that there's something holding the galaxy together. There's gravity, keeping it from throwing the stars out into space. So then scientists said, oh, well, that's cool. We can do something interesting. We can measure how fast it's spinning, and then we can count up all the stars and we can ask, is there enough gravity to hold the galaxy together, right? Based on how fast it's spinning. So they went off and they measured this. And what they discovered is that these galaxies are spinning way too fast. Like there just isn't enough gravity to hold them together based on all the stars that we could see. But on the other hand, they're not throwing their stars out into space. They're basically holding themselves together. So what's the story? What is holding these galaxies together? There isn't enough gravity just from the stars to hold them together if they're spinning this fast. So scientists thought, well, maybe there's something else out there that adds gravity, something invisible, something we can't see, but has gravity, has mass, has matter. So it adds to the gravity and can hold the galaxy together. This is the idea of dark matter. Now, dark matter is not actually literally dark, like a cloud of it in front of you wouldn't block your view. Instead, it's more invisible than dark. And by dark matter or invisibility, let's talk about what that really means, like microscopically. The way that you can interact with something, the way you can know something is there or see something is by using one of the four fundamental forces of nature. So for example, the Earth holds you onto it using its gravity, right? Another force that you're familiar with is electromagnetism. This is responsible for light. The reason the sun glows and it bounces its light off of things and into your eyes is because of electromagnetism. Things that don't feel electromagnetism are invisible. Light passes right through them. Then there's also the weak force and the strong force. So dark matter, we know that it feels gravity. It was invented as an idea to explain the missing gravity. But we think it doesn't feel electromagnetism because light passes right through it. It doesn't give off light or reflect any light. It also doesn't seem to feel the weak force or the strong force. So we have no way to interact with dark matter other than gravity. I mean, we've tried everything. We've even tried emailing it. We've tried Facebook. It's totally ghosted us on social media. The other incredible thing about dark matter is that it's not just a little bit of stuff that you need. Like to explain how the galaxies are spinning, you have to add a huge amount of dark matter, like equivalent to all the stars that are in the galaxy 5 times over. That's how fast these galaxies are spinning. It turns out these galaxies, they're mostly dark matter. It's like you're looking at a cupcake and you've only been seeing the sprinkles the whole time without realizing there's this enormous cupcake underneath holding it together. So 5% of the universe is me and you and hamsters and lava and pies and chocolate. 27% of the universe is this stuff we only recently discovered called dark matter. Now, this is a big idea to say that like more than a quarter of the universe is this new weird thing that's also invisible. Seems kind of suspicious, and people were tentative to believe in it. It took decades before scientists were convinced it was real. And one way they convinced themselves was they found other ways to see dark matter other than just galaxies spinning. One way you can see dark matter is seeing its effect on light. So matter bends space like everything else. You know, the reason that the Earth goes around the sun is because the sun bends the space around it. So the Earth moves around it sort of like, you know, like a toilet bowl. And so dark matter has mass, and so it bends space as well. And so if there's a huge blob of dark matter between us and another galaxy, then light passing through that dark matter will get bent as it goes through, as if there was like a giant lens in space, a giant invisible lens. So what happens to a photon shooting off from the galaxy in one direction? It could get bent towards your telescope. And a photon shooting off in another direction from the same galaxy could also get bent towards your telescope, which means you can see the same galaxy if you look in two different directions in the sky. And we look in the sky and we actually see this. We see the same galaxy twice, which means either, wow, enormous coincidence, the same galaxy exists, right, twice in the universe near each other, or there's a huge blob of stuff that's distorting our view, that's lensing it, that's splitting the photons and bringing them back so that we see two versions of this thing. So that's sort of amazing. Another way that we know about dark matter, and we're convinced that it's real, is that we saw an incredible event in the universe. We saw two galaxies colliding with each other. Now, galaxies have normal matter, and they also have dark matter. Well, what happens when they collide? Remember that dark matter doesn't feel any of the forces. The reason that you don't fall through the floor, or the reason that when you touch the table, your finger doesn't go through it, is because of electromagnetism. The electrons in your finger are repelling the next one. If you didn't feel that, your hand could pass right through itself. So when this collision happened, the normal matter smashed into itself, big collisions, but the dark matter passes right through. Now it does feel gravity, but gravity is very, very weak and not enough to stop it from passing right through each other itself. So we can see this huge explosion in the sky, and we can see, because of gravitational lensing on galaxies behind it, where the dark matter is. So we can tell that the dark matter got separated from the normal matter. It passed right through out the other side. This is called the bullet cluster. You can look up pictures of it. And this tells us something very important, that dark matter really is matter. It's its own kind of stuff. You can separate it from normal matter. You don't always find it together. It's not just like, oh, we misunderstood what gravity is or something. We really have discovered that there's another kind of stuff out there that's invisible, and most of the universe is made out of it. But we still don't know, like, what is it? You know, we know that it's there. We know there's a lot of it. We know that it's invisible. We just don't know, like, is it made out of particles the way we are? Is it made out of something totally weird and different we've never imagined? I kind of hope so. That would be a really fun discovery if so. You know, we don't know what it's capable of. We know it doesn't feel our forces. It might be that some of it feels its own new kind of forces. Maybe it can, like, come together and make weird little dark matter molecules and dark matter chemistry, and maybe even dark matter life. For all we know, the universe could be filled with, like, dark matter people, right? And maybe they just don't understand what we are, or what, you know, who we are, for all we know. So 5% of the universe is the stuff that we're familiar with. 27% is dark matter. If we're going to talk about, like, what is the universe made out of, we have to at least get above 50%, right? So let's talk about this last piece, this huge chunk of the universe, the 68%. This is something we call dark energy. But dark energy is just science code for, we really have no idea what's going on with this piece. You know, the only relationship between dark matter and dark energy is that word, dark. Otherwise, they're totally separate ideas in physics, where dark just means, like, we're kind of clueless still. It's mysterious to us. So how could we possibly know that 2/3 of the universe is something we don't know anything about? Well, it started when people were thinking about the history of the universe and the future of the universe. So here's a quick history of what's happened in the universe so far. There's a big bang, everything flew out, right? It used to be really hot and dense, and then things expanded and cooled. And instead of having, like, really hot burning plasma everywhere, things clumped together and formed galaxies and planets, and we got cats and all sorts of good stuff. So that's where we are now. And people were wondering, well, is this going to keep going? You know, stuff is flying away from itself. The universe is expanding. How long can it do that for? People thought maybe one possibility is that there's so much gravity from all the stuff in the universe, the galaxies and the planets are all pulling on each other. Maybe instead of expanding out forever, it's going to stop. It's going to slow down, stop, and then come back and crunch back together into, like, a reverse Big Bang. This was one idea for the possible future of our universe. It's called the Big Crunch. That's if there was, like, a lot of gravity to pull things together. Another possibility was that there wasn't enough gravity to pull things together, and things would slow down as they expanded because there is some gravity, but there wasn't enough to stop it. And things would just sort of like drift out forever, getting further and further apart, colder and colder, until eventually things are so spread out. We call that the heat death of the universe. So those are the two possibilities we thought about. It's like 20 years ago, people were wondering, is it option A, heat, a big crunch, or option B, heat death? Which is the fate of the universe? So they went out to measure this, and they did it by looking at supernovas, type 1a supernova, how they exploded, which lets us measure the distance to things and also the speed at which things are moving away from us. And what they discovered is that the universe said no to option A, the big crunch, no also to option B, the heat death. It went for secret option C. And this is my favorite moment in science, when the universe says, oh, you silly humans. The answer is something you didn't even imagine. So what it turns out is happening is that the universe is expanding, but we were wondering, is that expansion slowing down quickly, or is it slowing down slowly? Turns out it's not slowing down at all. The expansion of the universe is getting faster and faster every year. So that galaxy that's moving away from you, gravity is not slowing down how fast it's moving away from you. Something is speeding up how fast it's moving away from us. Something is pushing that galaxy away from us. What could be doing that? What is capable of pulling two galaxies apart from each other? And remember, galaxies have hundreds of billions of stars in them. We're talking about incredible amounts of matter. What is capable of pushing them apart, accelerating them apart? We really just don't know. We're at the point where we have seen that this is happening. We've given it a fancy name called dark energy, but we don't have any idea for what could be doing it, right? All we know is that it's happening, and it's happening faster and faster every year, which means that galaxies you see out there in the night sky are moving away from us, and they're moving away from us faster and faster. In fact, they're moving away from us so quickly, they are creating new space between us and those galaxies. It's not just that they're flying through space, but it's literally creating new space between us and those galaxies. And there's no speed limit to how fast you can make new space, which means that some of those galaxies are moving away from us faster than the speed of light. And that means something sort of mind-boggling, which is, imagine a photon leaving one of those galaxies and coming towards us. If new space is being made between us and that galaxy faster than light can go through it, that photon will never get here. It will fly forever into infinite future and never arrive. It's sort of like if Usain Bolt is running towards you, but somebody's putting down new track in front of him faster than he's running, he's never going to get to you, right? Or if you're on one of those moving walkways and you're going the wrong direction and you're moving slower than the walkway, you're not getting anywhere. That's the way the universe is, which means sometime far, far in the future, the night sky will be pretty dark. You know, all those galaxies that we can see today, they are literally disappearing. They're vanishing off the edge of the part of the universe that we can see. Or another way to think about it is that the fraction of the universe that we can see is getting smaller and smaller every year. Now, literally, we can see to further distances, but things are flying away from us faster than our observable universe is growing. So we can see fewer and fewer things, a smaller fraction of the universe. And, you know, before you think, ooh, I'm glad we live now when we can see most of the universe, remember that we live 14 billion years after the beginning of the universe. What used to be in our night sky and is now gone forever? We don't know, and we might never know, because it's literally gone forever outside of our observable universe. All right, so here's a summary of the universe as we know it. There's a pie chart, right? 5% of the universe is the stuff that we have been studying and trying to understand for, 1,000 years or however long you think we've been doing science. About 50 years ago, we discovered that a huge chunk of the universe, 27% of it, is made of some new, invisible, weird kind of matter. We still don't really understand what it's made out of. And about 20 years ago, we learned that most of the energy in the universe is not actually in the form of matter at all. It's not in me or you or in cupcakes. It's in this weird new thing that's accelerating how fast the universe expands. It's creating new space between us and other galaxies, and we don't know really anything about it. And I don't say this to run science down. I'm not saying, boy, science hasn't done its job. I'm saying, wow, look at the incredible discoveries that are ahead. We think about the universe a certain way because of the way we've learned about it so far. But we started out learning about the universe and learning about a very unusual bit, right? This bit that you and I are made out of is very unusual. We call it normal matter, but it's really dark matter that's the normal matter. We're the weird stuff, right? We're the sprinkles on top. And when you make a physics theory based on an unusual part of the universe, you might have gotten it all wrong. Imagine you were, for example, a biologist and you were studying elephants for 1,000 years, but you only ever looked at the tail. Do you think you'd have like a really good theory of the elephant? So that when you went around to look at the face of the elephant, you're like, oh yeah, I basically understand this also. That's sort of what we're doing right now with dark matter, because we're saying, oh, well, here's a new kind of matter. Maybe it's made out of particles the way our matter is. Maybe it is. Or maybe what we should do is throw out everything we thought we knew and start again, right? This is an opportunity to begin a revolution in physics, to say, boy, we really got started off on the wrong foot here. Let's look at everything new and try from scratch. And that's exciting because it means that you might find a whole new way to look at the universe, that in 500 years, children will think about the universe in a way that we find very confusing and complicated, right? The way children today know more about the nature of our solar system and the universe than leading scientists did 500 years ago, right? So the discoveries that lie ahead, I mean, they would blow my mind. If I could go 1,000 years in the future, I wouldn't go to a physics conference. I'd go to the library and take out astronomy books for 4-year-olds, because that's probably all I could understand. But we're doing everything we can to try to bring that future here today. We have space telescopes, we have gravitational wave detectors, we have particle accelerators to try to help us understand what is the nature of matter. But I feel very excited about it. I feel like we might discover any day something which really changes the basic nature of the universe as we understand it. And in the spirit of asking big questions, it might change the way we feel about the universe. Discovering that the universe is fundamentally random, the way quantum mechanics tells us, or that it might be infinite, really changed how we felt about our role in the universe. And these discoveries that are coming, I can't anticipate what they are, but because they're about big stuff and because there's so much we don't understand, it might really change the way we feel about life and how to live it. And tonight I've told you, or this morning, I've told you about one question: what is the universe made out of? But there's no shortage of really basic questions that we don't have answers to. Things like, what is space? You might think, oh, space is nothing. It's the emptiness. It's the stage on which the universe happens, right? Well, that's what Isaac Newton thought. Turns out space is more complicated because space can do things like expand, right? That's what dark energy is doing. Space can bend. That's what gravity is, it turns out. And space can also ripple. We've seen wiggles in space itself. Those are gravitational waves. This last one is a joke. Space can't do cartwheels. I mean, as far as we know. We also don't understand what time is. We know that time is related to space because of special relativity, but we don't understand, like, why can you move back and forth in space, but not in time? Why does time only flow forwards? We're at the very beginning of even understanding this. It's, we sound like the Greeks, sitting there eating olives and asking like crazy basic questions about the universe because we've made no progress since then. We don't understand really what time is at all. We don't even understand how many dimensions there are to space. It might be that there's 3 ways to move, like forward, backwards, left, right, up, down. It might be that there are more, that there are other weird ways to wiggle through space. Space might have 11 dimensions. Like, try to hold that in your mind. It's really hard because you are used to the universe in a certain way. You grew up in the universe that makes a certain kind of sense to you. But one of the biggest lessons in physics is that the universe is the way that the universe makes sense to you is not the way the universe works. And if we need to very carefully like use our knowledge and our smarts to try to understand the truth about reality instead of just making assumptions and relying on our intuition. And the key is being curious, is asking questions and exploring the unknown, and knowing what we don't know is the first step. And so I think it's actually a very exciting time in science because we know that we know very little. We can measure very precisely that we know a very tiny bit of the universe, which guarantees exciting discoveries. So we talk about this in our book and in our latest book, Frequently Asked Questions, and twice a week on the podcast if you're excited about this stuff. So thanks very much for listening to me talk about the things I'm enthusiastic about. I really appreciate your attention.
All right.
Wow.
Wow, that's a lot to process. It's just too much, but too little, too much.
Wow. And we're joined by our founder, we are Jeff.
Dr. Jeffrey Bunkin.
I made it. Yeah, thank you so much. Thank you so much for that talk, Professor Whiteson. So, I'm by the way po, sa mga to all those who are like like part of our of the audience, I'm Jeffrey Bunkin. I'm the founder and Chief Executive Officer of Filipino Science Hub. So yeah, I was able to catch like a very good part of the talk, and I hope that our audience members have prepared their questions, because it's fairly rare, like that we actually get to invite like somebody like Professor Whiteson to Filipino Science Hub. So all right. So do we have questions from Zoom or from...
Yeah, I think people are still stunned about everything.
Okay, so if they don't have questions,
Very first time, nobody has questions.
Okay, so if they don't have questions,
we're really maimed about this.
Let me ask the first question. So Daniel, I actually have watched like a number of videos when it comes to like astronomy, and in particular what piqued my attention was it was, I think, a video documentary about like how scientists are modeling the universe. And that I heard this phrase saying that the universe is a conscious universe. Could you make some comments about that, about like how things are moving, and like how dark energy and dark matter might be related to that? I mean, like people are coming up with a bunch of those, like speculations. Yeah.
Yeah. Well, there's a lot of really fun ideas. Something that's exciting about science is that it gives us the feeling like maybe we can understand everything. And one of the big questions we'd like to understand is like, why are we here, in the sense of like, why am I inside this body?
Yeah.
What does it mean? Do I have free will? Am I part of the universe? Is the universe part of me? And people try to answer this question sometimes from the point of view of physics, of say like, could you take apart a human body, not literally, but like understand everything that's happening inside of it and then predict what's happening? If I knew everything about what was going on inside you, could I predict what you're going to do tomorrow? Because it seems like the universe is kind of predictable. Like if I throw a ball, it follows rules and I can predict where it's going to go. If I hit two balls against each other, I can predict what's going to happen. So aren't you essentially just a huge complicated pile of balls bouncing against each other? And in theory, I mean, it's impossible in practice, but in theory, if I had a big enough computer, shouldn't I be able to predict what you're doing? And if that's true, does that mean that like you don't actually make choices? You're not really alive there driving your own body. So I think sometimes people try to ask those questions using physics, but it's tricky, right? It's very tricky because it turns out at the smallest scale, like the universe isn't just a bunch of balls bouncing against each other in a way that we can predict. The universe is kind of random. Like there's quantum mechanics, right? So, electrons in your brain don't just fly in one direction. Sometimes they bounce this way, sometimes they bounce that way. We cannot predict what's going to happen. It still follows rules, but sort of in a different way that can't be predicted as easily. We don't really know what that means. We don't know. Does that mean that you can't be predicted? Does that mean that you really do have free will? Is there room in there for the person to be guiding this? Or, as you were saying, maybe that's what consciousness is. Maybe the whole universe is conscious, and that's just what we are experiencing. The thing I love about these questions is that there's a close connection between the physics and the philosophy.
Yep.
You ask hard questions and you think about like what it means. So we are very far away from understanding consciousness or what physics can tell us about it. But it's exactly the kind of question that we should be thinking about. It's a lot of fun.
All right. Are there questions coming from the floor?
Tita Connie, are you saying something?
You're on mute.
I was just thinking, Dr. Whiteson, Daniel, that I kind of imagining that Isaac Asimov would be talking like how you talk right now. The metaphysics
Isaac Asimov is one of my favorite
everything.
authors.
Yeah, I was just like wondering about because of this this huge amount of information that we don't know. I was just wondering if our current tools, our mathematical models or quantum models, are able to will suffice or be enough to try to understand what we really don't know. Or because you were saying earlier about like all these language, because we're trying to fit in everything to the language that we know, which are the developed quantum models about the universe. And I don't know if they are enough, or should we develop another language to try to understand or make it less complicated? Because you have shown this like entire equation that wouldn't fit into a t-shirt. So are we trying to do that?
Question. We know that the theories we have work pretty well, and we've tested them at colliders. So like not just describing the kind of things that we experience in our everyday life, but really high energy, very intense environments, similar to what happened like very early after the beginning of the universe. And they still work very well up to there, but we know that they will fail eventually, because we know that, for example, they don't describe dark matter, and we don't understand gravity at a quantum level. So we know eventually they will fail. What we don't know is like, do they need to be corrected a little bit, or do we need a complete revolution and a completely new idea? We don't know. And one problem is that we can't really access those scenarios. Like in order to understand where our theories fail, we need to find really extreme cases like the very early universe, but that's all gone, or inside black holes, or in the heart of neutron stars. That's where the clues are about the deep truth about the universe, but they're very, very hard to find, unfortunately.
Yeah.
Yes. So what went before the Big Bang? What was there before the Big Bang?
Yeah,
it was always a question I hear whenever
It's a great question, and it's a question that we answer in our book, Frequently Asked Questions About the Universe.
You did?
Because everybody asks that question, because it's a great question.
Yeah.
Because we all want to know, right?
I am gonna get that book. Is there an audiobook version of that, Daniel?
There is, yeah. Jorge and
All right.
read it,
I'm getting it. So actually, I have a question. So Daniel, back in 2015, the first time that astrophysicists detected gravitational waves, I will never forget that, because I was at Argonne National Laboratory, and like some of our folks back there were actually, I think, to a certain extent involved in the LIGO project. So are you aware of existing efforts at the moment to like study or detect dark energy and dark matter? Is there such effort ongoing?
Yeah. Oh, there's a huge program to try to understand what dark matter is.
Yeah.
We are hoping that dark matter is like something we can discover, and we don't know what it is. And so one thing we do is we say, well, let's just assume it's the simplest idea. Like, what if dark matter is just one kind of particle? And what if it what if it's not totally invisible? What if it like sometimes bumps into our kind of matter? So they have these experiments underground with like huge tanks of xenon, liquid xenon, just sitting there waiting for dark matter to come through and like bump into one of those xenon atoms. And if it does, then they'll see it. So
Oh.
they've been running this for years, making bigger and bigger tanks of xenon. So far, they haven't seen anything, but we don't know.
And that makes me quite curious. So these are liquid xenon, and what makes how was that designed? Like, how was that supposed to, how was that, like, like made to be like specific, like for detecting dark matter? Perhaps you might have covered this earlier.
No, not at all.
Yeah, what's special about xenon? Yeah,
Xenon is very inert, right? It's a noble gas.
Oh.
And mostly it'll just sit there. It will hardly interact with anything.
Okay.
But sometimes something might come along and knock off one of the electrons on the xenon atom.
And
And
so that will make a ripple?
Yeah, it would make like a little flash. The energy from that electron would give off a photon and you could see it. So mostly it's like a big dark camera and they're waiting for a little dot. And they bury the camera deep underground so nothing else can get to it. But dark matter should be able to go through the ground.
Yeah.
So it's just like burying a camera a mile underground and leaving it on and coming back to see if there were any little bright flashes. And if you see any, you think, oh, well, something must have made it all the way through the ground and hit my camera. So it's basically a big dark matter camera made out of xenon. So far, they haven't seen anything. And we're looking for dark matter in other ways. People are wondering, like, maybe dark matter is made out of strange black holes that were created in the very early universe and are still around. They might be like small black holes floating out there in space that are otherwise invisible. That's one idea of dark matter. Another idea for dark matter is it might be some new weird heavy kind of photon, like a kind of photon that has mass, a new thing that we haven't ever seen before. So people are being really creative, coming up with, silly ideas for what dark matter might be. I suspect that none of those ideas are right, and that dark matter is something else even weirder than we've imagined, because it's sort of hard to think outside the box. We tend to think about new versions of what we've had before. Like, think about what happens if you eat a new fruit you've never had before. You're like, oh, it's kind of like an orange with a little bit of a cherry in it. You think about it in terms of what you already know. So that's what we're doing with dark matter. We're like, maybe it's like this, but a little different. But if dark matter is really different, it's going to be hard for us to imagine it. So it might take us a while to figure it out. It might take like new, young, smart people, like hopefully the young students are listening, to have creative new ideas.
Yeah, and we actually have like a total of about like 50 participants today.
Great.
So yeah, so by the way, there's a question that was sent to me directly. So I would like to read this like on her behalf. She said that her internet is fluctuating. So she actually mentioned like a phrase like from the Bible. It says like, Matthew 24:35, heaven and earth will pass away. If this is true, can we predict how long will the universe exist? So I think she's asking about, okay,
it's a great question.
when will things end?
We don't know. One reason we don't know is that this process that's pulling the galaxies apart, this is not something we understand.
Yep.
So you might say, well, let's just assume it's going to keep going the way that it's going. In that case, the universe is just going to keep expanding forever. There's no end. It's just going to keep going. And eventually all the matter will fall into black holes, which will be very, very far apart from each other. And so the whole universe will just be like dark with black holes in it. That's in like, trillions and trillions of years. But we don't know what dark energy will do because we don't understand it. So we can't confidently predict it. It's like if you look at the stock market and you have no idea, is Bitcoin going to go up or down? If you don't understand it at all, you can't really predict confidently. So it might be that it changes direction, that dark matter stops and turns around and comes back and squeezes the universe, dark energy, squeezes the universe down into a dense state again. We just don't know. We'll have to wait and see.
Yep. I have a question here from Jean Robin Hentolea. He was asking, I don't know if he's in the room or he want to ask this directly, but he was asking about how do we attach those numbers? Because you were saying about this like 68%, 2/3, and how do we attach the numbers on the composition of the universe? I mean, how
do we know those numbers? Yeah, that's a great question. We actually know each of those numbers separately in several different ways. We've measured them in different ways, so we're pretty confident. One way is by just adding up the amount of stuff that we see. Like we can tell how much dark matter there is based on how fast galaxies are spinning, because we know how much there has to be to hold them together. So that's a way we can know how much dark matter there is. We can tell how much energy there is in dark energy because we measure how fast the universe is expanding. We can also measure these things in a totally different way, which is by looking at baby pictures of the universe. We can see all the way back to when the universe was just 380,000 years old. The light from that is still bouncing around. We can capture it. It's called the cosmic microwave background radiation. And light from the very early universe tells us a lot about how much matter and how much dark matter and how much dark energy there was, based on like how the plasma was back then, how it was sloshing around and how it was rippling. And so by measuring those ripples, we can measure those fractions very precisely. It's a totally separate measurement from a different age of the universe, and they line up very, very well. So that gives us a lot of confidence that that's really what's going on.
Right. And there's another question. So, are the books presented not available in any bookstores in the Philippines? Ate Lindy,
I'm not sure if they must be available.
I think there's one on Shopee. Actually, we're planning on giving away a book right at the end of the webinar. So just
That's good news.
Yep, just hang in there.
You'll know what we don't know. so Daniel, once you got, like once there's a major breakthrough about dark matter, are you gonna write like a follow-up book? Now this is what we know.
We know some things.
Yeah. I have a question.
All right.
Yeah. Also, Daniel, are you somehow involved in the discovery of some of these new particles, or if not, what kind of research are you involved in right now? If you could briefly or vaguely describe, if it's confidential.
Who knows? Like someone from the audience could become your graduate student.
Just for the appreciation of the kids that are here today who maybe want to pursue a career in physics. So.
Sure. Well, my research is I work at the collider at CERN. So we smash protons together. And what we're doing is looking for weird new particles. When we smash protons together, we don't just like rearrange the insides of the protons into new bits. We destroy the protons completely. So like the proton energy turns into like a little fireball. And from that, you can make any particle that exists in the universe. So we're like looking for new weird particles by smashing protons together. So that's what my personal research is day to day, is to look through the data from the collider to try to find weird stuff that we didn't expect to be there, hoping to find something which, surprises everybody. So that's what I work on.
Nice.
Yeah, because these new particles that, the physicists discover, can you cite some technologies or like any applications that they're being used nowadays?
Yeah, so we work at CERN, where they built the collider, and it uses like very low temperature superconducting magnets to bend the particles around in a circle, because the particles are going at the speed of light almost, and so you need very powerful magnets to bend them around. And we have huge amounts of data which we share all over the world. And the World Wide Web was actually invented at CERN, so we could more easily coordinate and share our data
I didn't know that.
with each other. Yeah. So particle physicists are often on the cutting edge of doing this kind of stuff. And then
CERN is based in Europe, right?
Yeah,
in Geneva.
It's in Geneva, exactly, right on the border between France and Switzerland.
Thank you.
Another question from Renee Alvin Okendo. If the universe is expanding fast, how long will it take for the Earth to completely drift away from the sun?
Good question.
Yeah.
Good question. You don't need to worry. So the universe is expanding, and then expansion is happening everywhere. It's between galaxies. It's also between stars. It's also between planets. It's also between atoms. So the space in your body is expanding right now. The reason that doesn't blow you apart is that the forces that are holding your body together are stronger. And also the gravity that's holding you to Earth is stronger than dark energy. The gravity that's holding the sun and the Earth together is stronger. So gravity is pretty weak, but when things are close together, it's more powerful than dark energy. When things are really far apart, like between galaxies, that's when dark energy wins. So dark energy is winning the competition with gravity for very big stuff between galaxies, but not yet for very small stuff like solar systems and planets and you. So we think that the Earth is not going to get yanked away from the sun in the next few billion years. And anyway, the sun is only going to burn for another 4.5 billion years. So we'll have problems before we get to dark energy anyway. We need to find a new place to live.
Yeah, Daniel, I think you have some fans in the audience. So Alan Brutus, I don't know if he's a student or if he's an like a STEM educator, but he's asking, is there a possibility for Professor Daniel to have a book tour in the Philippines?
Are there any hosts out there?
Yeah.
Well, that's nice. Thank you.
Yeah.
I'm sure it'd be a lot of fun.
Are you doing book tours anyway? Are you doing book tours?
No, not right now. Because
okay.
of the pandemic, we basically didn't do a tour for our second book. So mostly we're staying at home.
Yeah, we can do it offline.
All right. Yeah. And then there's another one, I think.
From Mark Owen Lovino, in one of his final theories, Hawking made some remarks on the multiverse hypothesis. This is very popular right now. Based on eternal inflation, what are your opinions on the multiverse? Is it absurd or worth considering a thought?
It's definitely worth considering, and not just because I like watching Spider-Man or Doctor Strange. It's exactly the kind of creative thinking we need to be doing. Like, maybe the universe is far stranger than we imagine, and we need to exercise our brains and thinking about crazy stuff. It's certainly possible that the multiverse is real, that either there are other pocket universes out there that are very far away from ours, that we could someday, either we could maybe never interact with, but they're out there. Or it could be that there are different kinds of universes with different physical laws that all exist at the same time. That might be like impossible to move between. There's this idea of the quantum multiverse, where, when a quantum particle, has two possibilities for what it can do. Maybe it can go left or maybe it can go right. One theory of quantum mechanics says, well, the universe picks and it's random. Another theory, it says the universe doesn't pick, it does both. It splits, and you get one universe where the electron went left, another universe where the electron went right. And that's called the quantum multiverse. And that idea, we are in one of those universes, and there's an infinite number because there's so many particles constantly doing so many things. And some people think that's not just like an idea, that it's real, that those universes are really out there, sort of like not in our space or on top of us, but they exist in a different way. So it's a very powerful idea, one we should definitely be using and thinking about to help us understand this crazy universe. Probably the reality of the universe is even crazier than anything Marvel imagined.
So Daniel, from a career guidance standpoint, like if our students in the audience would like to get involved, like say like in the study of fundamental physics of particles, as well as dark energy and dark matter, could you speak about like different STEM specializations that they can pursue?
Yeah, sure.
To get involved, yeah.
First of all, if this kind of stuff excites you, awesome. I think that people should listen to what's inside their minds. Like, what are the questions that you want to ask? What are your questions? Because this kind of study, it requires you to really be curious. Remember that everything anybody's learned in science is because somebody decided, I'm going to study bats, or I'm going to study planets, or I'm going to study this molecule because I want to know the answer. Science is not like some institution pumping out knowledge. It's just a bunch of curious people. So figure out what you're most curious about. If this kind of stuff is what you're curious about, then, a degree in physics is the right way to go. And, that involves a lot of mathematics. And so if you enjoy mathematics and think it's a fun way to think about the universe and solve problems, quantum mechanics. So a degree in physics is a good way to get started. After that, if you're excited about it, you should try doing some research, because research is pretty different from classwork. Classwork is like, here's a problem people have solved 1,000 times. Now you need to solve it, but it has a solution. Research is like, well, we don't know what we're doing. We're sort of poking around out there. It's exploration. You might find something amazing, or you might not make any progress at all for months and months and months. And so it's very different. And you got to try it to see if you like it. It really takes like trying it. For me, I tried lots of different kinds of physics before I found what I liked. I was excited about the idea of physics, and I went into plasma physics to try to work on fusion energy because I thought that's cool, right? But I didn't actually enjoy like the day-to-day work of it. It was like vacuum pumps and magnets, and it just wasn't fun. And then the next summer I did laser physics. I thought that's going to be cool, but I spent the whole summer in a basement trying to get a laser to work. And a laser is made of like 500 pieces, each of which work 99% of the time, which means something's always breaking. So I spent a whole summer like trying to get this laser to work, and it worked for like 19 seconds the whole summer. So that wasn't for me. And then I discovered particle physics, and particle physics is mostly about analyzing data, writing computer programs, doing simulations. And I was also a computer person. I liked writing programs. So for me, it was a good fit. So you have to find the kind of questions you're excited about, and also the kind of the field that like where the day-to-day work is fun for you, because we're not making big discoveries every day. We're not solving mysteries of the universe. Mostly every day I write computer programs. And for me, that's really fun. I like writing programs. So you got to find what's exciting for you and what's fun to do day to day.
So Daniel actually raised a very important point about a career, right? About picking a career. So sometimes it actually takes several trials to figure out, what it is that, gets you excited and gives you the fulfillment that you're looking for. So by the way, and then another thing, I think Daniel, you're the right person to ask this question. The Philippines doesn't have its own NASA, right? So from a practical standpoint, why do countries say like the US like have institutions like NASA? Like from a practical standpoint, like what would countries benefit from, from funding, these institutions? Why do we have to look out there?
Yeah, it's a good question. I think there's a lot of different answers. One is just purely to know, not everything we do in life has to be economically productive. Some things we do because that's just what life is. When you stop working and you're done for the day, what do you want to do with your life? You watch movies or you make art. That's really what life is in the end. You laugh with your friends. And for some of us, pursuing knowledge is that thing. That's what life is about. On the other hand, I strongly believe that basic research is good economic sense. Like if you create NASA or particle colliders or whatever, you're going to train people to think deeply, and they're going to come up with fun ideas, and that's going to lead to economic development. Why do we have the World Wide Web? Because people needed it at CERN, and it changed the way we live. Why do we have transistors? Every invention which transformed our society and made us all wealthier came from basic research, which is not like go and invent something right now. It's like, here's a bunch of money, think about hard problems. So paying people to be curious about the universe and think about hard problems pays for itself. If you have the money to spare, invest it in education and basic research, and it will lead to economic wealth and intellectual wealth. It's just the right, I'm biased, but I think it's the right way to spend money. I wish we all spent a lot more money on that and less on aircraft carriers.
Yeah, I can very well relate to it. There's a reason why I left Argonne National Laboratory.
yeah, defense industry, right? I grew up in Los Alamos, and that's a lot of weapons research. One of the reasons I ended up in particle physics was that I didn't want to work on anything that could be used to kill people.
Yep. All right. Are there other questions?
I have a question here on YouTube from Christian Harold Ramirez. Dr. Whiteson, where does the Higgs boson fit into the 12 quarks and leptins?
Oh, great question.
Yeah.
Yeah, so the Higgs boson is a special particle. The 12 particles that I told you about, those are the matter particles. They make up stuff. The Higgs boson is different. It's a particle that makes those particles have some mass. So if we lived in a universe without the Higgs, then the electron and all the quarks, they would be massless like the photon. They would fly around the universe at the speed of light. But instead, we have something in the universe called the Higgs field, this mysterious thing that fills the whole universe and changes how particles fly through space. So an electron, instead of flying through space at the speed of light, moves through the Higgs field that's constantly tugging on it and changing the way it moves. And it changes the way an electron moves in exactly the same way as if that electron had a little bit of stuff to it, as if it had mass. So the Higgs particle is the Higgs field that fills space. The Higgs particle is like an excited state of that field, like a little spot in that field where there's a lot of energy, it's buzzing. And so this is something we discovered at the Large Hadron Collider about 10 years ago. It gives all these particles mass. And you might think, well, doesn't that explain how particles have mass? It doesn't really, because it doesn't tell us, like, why does it give the electron a little bit of mass and the muon a lot of mass and the tau even more mass? We don't understand that. We understand that particles do get mass, but we don't understand why the Higgs gives some of them a lot of mass and some of them almost none.
Yep.
Do we have other questions?
From Alex Tumula. Do you think a degree in chemistry is also good in pursuing astronomy? Thank you very much.
Yeah, I think as an undergraduate, you just need to learn to, think scientifically. And from there, you can go and do research in lots of different fields. These days, because astronomy is discovering planets around other stars, they're at the point where they're doing astrochemistry. They're thinking about, like, what are the gases in planetary atmospheres around what are the gases in atmospheres on planets that go around other stars? We can actually see that because we see light from those suns pass through the atmosphere and come to Earth, and we can tell by what was absorbed in that light, we can tell what's in the atmosphere. So understanding chemistry will help you, like, do studies like that. Think about, are there signs of life on these planets?
Yeah.
The kind of thing we'll be able to do with the next generation of space telescopes.
All right. So I think that's all I have.
All right. So
yeah,
then
I don't see any more questions
Right.
on.
yeah. So Ate
YouTube.
Lindy, would you like to actually talk about, like that?
Right. So, like what I mentioned earlier, I'm just fangirling here. Yeah. So, like what I mentioned earlier, we would like to give away one of Dr. Whiteson's book, Explain the Universe. Oh no, sorry. We have no idea. That's what I meant. Explain the Universe is a podcast. Sorry.
Lindy's speaking out because she's a big fan, and her husband as well. So yeah, they listen
Sorry.
to the podcast and they read
Okay.
his books.
Yeah.
Actually, so before we end, I just have one question, because this is one very important thing which I noticed, like, in how Daniel presented his talk. It is very obvious that you are a science communicator. Could you make a comment about why it is very important for STEM, like for those who would specialize in STEM, to also be great at communicating?
Yeah, it's a lot of fun, I think, to share your work with the public. I also think it's important to have ideas. Like, you need to be able to explain what you're doing, not just to the public, but to the folks at the lab next door. Maybe they have an idea to solve the problem in your research. These days, we're doing a lot of cross-disciplinary work, like computer scientists using machine learning to solve problems in physics. That happens because people know how to talk to each other without just using big, complicated words. They can understand the basic ideas and explain the questions. So learning how to communicate what you're doing is very important for doing it better, for getting new ideas, and also for explaining to the public. Like, in the end, all of this stuff is paid for by the public. It's all tax dollars. So I think people deserve to understand, why are we doing this? Why is it exciting? And also, everybody deserves to share in it. It's something that really is for everybody. It's not just for a few people to get to think deeply about the universe. Everybody deserves to understand what we're doing and why we're doing it.
All right. So I didn't realize that Janice already asked that question earlier. That's the price I have to pay for being late. So Daniel, we're
No, I
giving
think
away.
it's a good question because there are so many high school teachers here listening to us right now, and he's the best person to give advice to our high school teachers to really encourage students to like physics, because it's a really complex subject.
Synthesizing and reflecting on synthesizing from what Daniel said, from the things that Daniel said earlier. One very important thing that I liked about what he said when he was talking about like research, right? Like how different it is from traditional education, where you're being given a problem and it's been solved countless number of times, and then there's a solution to it, like doing what he does, really studying what's out there. It's a different kind of problem, right? And like you have to be very creative when it comes to coming up with approaches, which is I also like quite timely. I studied like business innovation, which talks about creativity from Rice University, Daniels. There's a lot of parallels out there. But anyways, so we're giving out a copy of your book. And we just like I'm gonna put you on the spot here. could you give us a question? Like just like a question out of something that you have mentioned during your talk, and whoever it is from Zoom and YouTube who could give like the fastest, the answer the quickest, like will get the book. So we're gonna give out two, one from YouTube and one from Zoom.
Can the hosts join too?
No.
I already have. Oh, you can't see.
Yeah, you can see it. You have to do it like a vlogger, ate.
And I already.
Sure. Yeah. All right. Should I ask the question
there's less competition in YouTube, guys. There are only many people there.
Should I go ahead with the question?
Sure.
All right. So I guess the question is, what fraction of the universe is made out of normal matter, like me and you and stars and hamsters? What fraction of the energy in the universe is in normal matter?
Ayan, may nauna na.
I see a.
All right. No one's answering from YouTube, so I guess we're only gonna give out like one copy.
There's a delay, so.
Oh yeah, there's a 30-second delay. Yeah, on YouTube. So
the answer is 5%.
Oh, there's someone answered. So what's the answer, Daniel?
It's 5%. Yeah.
All right.
Okay.
So who's our winner? Our winner from
YouTube is Christian Harold Ramirez.
Okay, and then from Zoom.
From Zoom, I think it's
Yeah.
Careful.
Tama, kuya.
Alexis?
No.
Eileen Santillan.
Eileen Santillan. So please, contact us at philscihub at gmail.com.
I'll take note of it.
We will we will coordinate with you, like how we how we can send the book. All right. So so at which book was it? Is it again that's available from Shopee?
We have no idea.
Yeah,
Is that the answer to my question, or is that all right? We have no idea. Okay, so congratulations, Christian and
Eileen.
Yes. Yes, perfect. So JP, we have a certificate of appreciation.
Oh yeah, we have to.
Yes.
Wait, let me just grab it.
Yeah, before we close.
Before we close, we would like to present this certificate of appreciation, because this is the only thing we can give. During this webinar, along with 50 participants this morning, we have no idea, a guide to the unknown universe, organized by the Filipino Science Hub and held by Zoom and YouTube Live on this 13th day of May. Today is Friday the 13th, and I hope good luck for everybody. And signed by yours truly and our CEO and founder, Dr. Jeffrey Camacho Bongkid. So in behalf of everybody here on Zoom and on YouTube, we would like to thank Dr. Daniel Whiteson for giving us the pleasure of knowing you and really appreciating how much what we don't know, what we don't have any idea of.
Well,
I
thank you
think like
very much.
everyone,
Pleasure to
yeah,
meet all of
everyone
you.
from Phil Sci Hub is a fan. So
All
thank you
right.
so much,
Have a good
Daniel. Yeah,
evening.
we hope, yeah.
Bye-bye.
Thank you,
so much.
Daniel.
Thank you, Daniel.
Thank you.
Oh, can we
everyone.
actually request for a photo for a photo
Photo op.
opportunity, like with
We're all-
all the participants, if that's okay, Daniel?
We are
Sure.
Just
all.
for a couple of seconds, yeah.
Let me just grab the gallery. All right.
All
On
right.
3, 1, 2, 3. All right. Yep. I think that's it.
All
All
right.
right.
All right,
All right.
thank
Thanks very much,
you.
everybody.
Daniel, thank you so much. Thank you, everyone.
It
Maraming
has
maraming
been an
salamat
honor
po sa
and
pagsama.
pleasure. Thank you very much.
Thank
Now
you.
I already posted the link for the Google form here on the chat box, and also I haven't posted it on YouTube. Wait.
All right.
Oh, there it is.
Yo, nandun na siya, kuya.
All right. So
Maraming salamat po sa
maraming
pagsama.
salamat po. Medyo nosebleed po tayo ngayong umaga. Pasensya niyo na po, but yeah.
Ako naman gabi na dito naubos na yung English ko. Oo,
Yeah,
pasensya
we
na po,
have to
naglo-loading
thank,
na yung utak. Ano yan?
we have to thank Ate Dindi for
For inviting
getting
our
contact with
speaker.
for getting contact with
And
Yeah.
thank you so
Dr.
much.
Daniel.
And thank you so much, everyone. So JP Onya po dialed in from Finland, and then Janice and Dr. Gibas from the US rin, from Kansas and from San Antonio. And Ate Didi, maraming salamat. Thank you so much, everyone po.
Yeah, and
Maraming salamat.
we have another webinar next
Week with
Saturday or Friday.
Saturday in the Philippines with
Okay.
Professor Elmer Mojica. So ayan, about action research naman yon. And then
About
another
action
one.
research.
And then another one on metrology. So there's on the 28th. So someone from the OST will deliver a webinar. Ayan.
Okay.
Maraming
Favorite ko yan. Oo.
Alin, which one?
Meteorology.
Metrology.
Oh,
Magsusukat.
Professor Sheila Rose. Professor Sheila is here.
Ma'am Sheila, magmi-meeting tayo soon. Mag-meeting tayo.
Ayan, nakakatuwa naman.
Maraming salamat po.
Congratulations.
Oo.
Yan.
Ayan, nagbago na ng apelyido si Ma'am. Sheila
Ito yung
Pastor
mga-
na siya.
Sheila Pastor.
Oo.
So, Pastor Sheila.
Ayan.
Ayan.
Ayan. Maraming salamat po muli sa inyo.
May debriefing ba, Jeff? Nakaalis na siya.
Oo, nakaalis na siya eh.
I think it's busy.
Oo. Okay na, matulog na tayo. Medyo lutang din ako. Maraming salamat.
Thank you, guys.
Thank you, everyone. Thank you, Mama Connie, Ate Ja, JP.
Good night.
Thank you, everyone.